Next subtopic is polarization in directrix. We have noticed that the main difference between a conductor and a dielectric lies in the availability of free electrons in the outermost atomic shells to conduct current. And although the charges in a dielectric are not able to move about freely, they are bound by finite forces, and we may certainly expect a displacement when external force is applied. Now, to understand the macroscopic effect of an electric field on a dielectric, consider an atom of the dielectric as consisting of positive and negative charges. The negative charge is an electron cloud surrounding the positively charged nucleus, as we can see in figure 5.6a. So in figure 5.6a, we have a positive nucleus surrounded by a cloud of negatively charged electrons. Now, a similar picture can be adopted for a dielectric molecule. We can treat the nuclei in molecules as point charges and the atomic or the electronic structure as a single cloud of negative charge. And since we have equal amounts of positive and negative charges, the whole atom or molecule is considered to be electrically neutral. Now, when an electric field is applied, the positive charge is displaced from its equilibrium position in the direction of the applied field. So the idea that we are having is quite simple. This was a positively charged electron or molecule. Okay, not positive charge. This is an electrically neutral atom or molecule. If you apply some field pointed in the direction of the arrow, then this will result in a charge distribution that will take a shape similar to this, whereby the positive is displaced from its equilibrium, and though it may not move to the farthest end because it's normally fixed, we might end up with having fewer electrons on that side and a higher concentration of electrons on the direction from where the electric field is coming from. So you might end up having higher concentration of electrons on this side, and therefore if you are to represent this atom in a new diagram, it would appear like you have one normal atom that still has some electrons surrounding a nucleus, but then there is some net effect of a negatively charged Q and a positively charged Q that forms a dipole. And that diagram can actually be seen in this diagram right here. So we are saying that when you apply some field on this electron, then you find some higher concentration of electron on the direction from where the electric field is coming from, and a lower concentration of electron from the direction in which the electric field is directed. And you're saying the end result is that this is equivalent to this. And as we have said, a dipole results from the displacement of the charges, and the dielectric is said to be polarized. So this alignment of charges, as I have explained, is considered to make the dielectric polarized. And we are saying now in the polarized state, the electron cloud is distorted by the applied electric field. The distorted charge distribution is equivalent by the principle of superposition to the distribution plus a dipole whose moment can be given by this value. If you remember, we already met the concept of dipole and its moment when you are discussing a dipole moment. And therefore, we are saying that this alignment of charge constitutes what we are calling a dipole, and dipole has the moment P, which can be obtained by the charge itself multiplied by the displacement or the distance vector between the two charges. And if there are n dipoles formed after the application of an electric field in an elemental volume dV, then the total dipole moment due to the electric field is going to be considered to be equivalent to the sum of the individual dipole moments that are formed due to the electric field. So this would give you equation 522. Now, in addition, we can develop another measure of intensity of the polarization by defining a polarization vector P, now capital, which is measured in coulombs per meter squared, which can be considered to be equivalent to the dipole moments per unit volume of the dielectric. That is the total number of dipole moments that we have obtained, K, from K is equals to 0, or K is equals to 1, to K is equals to N, then per unit volume, that is when we say limit small volume approaches 0, then you divide by dV. This gives you what we consider to be the polarization vector that is given or measured in coulombs per square meter. And you can always remember very easily that the dipole moment P small is considered to be in coulombs meter. Therefore, when you divide this by unit volume, which is measured in meter cubic, you can clearly see that this gives you coulombs per meter squared. And thus, we conclude that the major effect of electric field E on a dielectric is the creation of dipole moments that align themselves in the direction of electric field E. And this type of dielectric is said to be nonpolar. Examples of such materials that are said to be nonpolar is hydrogen, oxygen, nitrogen, and the rare gases. And what we know about nonpolar dielectric molecules is that they do not, the word is do not, possess dipoles until you apply some electric field. However, there are other types of molecules such as water, sulfur dioxide, hydrochloric acid, polyester that have some permanent or built-in dipoles that are randomly oriented as you can see here in figure 57A. So one dipole will face that direction, another one will face that direction, another one in this direction. At the end of the day, the material is said to be non-polarized, but itself is said to be polar. That is what we are saying here, that when there is no applied field, it is said to be non-polarized, but when you apply the field causes the dipole moments to experience a torque that tends to align the dipole in the direction. So if you apply a field, then all the dipoles that were arranged in a similar manner will all of them align themselves in one direction. And once they align themselves in one direction, that is the direction of the electric field, then they said to be polarized. We now attempt to calculate the field or the electric field due to a polarized dielectric. Having understood how a material gets polarized and the two different types of materials, one that is polar and the other one that is non-polar, then we want to find out what is the effect of the polarization to the applied electric field. Now we are going to consider the dielectric material as shown in this figure. We have a dielectric material that is in free space there, but this is a dielectric material. And if you remember, we said that the material is sometimes be considered an insulator, but it has different dielectric properties. Those properties are the ones that determine how well the electric field propagates or is sustained in that medium. Now we are saying that we consider that dielectric material as the one that is shown on figure 5.8 as consisting of dipoles. So we are considering a polar dielectric that consists of dipole with dipole moment P per unit volume. And according to equation 480 that I have just written here, the potential at an exterior point O due to the dipole moment P dV prime. So we are observing the potential at this point due to this elemental volume dV prime. We are saying that that potential can from this equation, which is 480, can be expressed as in equation 4524. Just to clarify how we get to this is that this was considered as a dipole moment, and we say that it is a small p. If we want to find the polarization vector P capital, we say that we say that the polarization vector P is obtained from the dipole moment, sum of them, divided by unit volume, and that gives you the this polarization vector, and this one is dipole moment. I think I should just bring this out there. And therefore, since in this question we had dipole moment, we can just multiply both sides by dV and by dV, and therefore we are ending up with a small, or the dipole moment replaced by polarization vector P and the unit volume dV. So that is what we have here, the polarization vector P and the elemental volume dV. So having clarified that point, therefore, is we can do some further derivation, which I'm going to skip just for the sake of time, and jump to the most important bit. You can always follow what we are trying to do here. And the most important thing that we want to mention is that we get just to rephrase, we are looking for the V at point O, and when you follow the derivation that we have skipped for the sake of time, we are able to observe that we have two terms that define the potential at point O. And remember where point O was? In our figure here, we were trying to find the potential at point O due to this elemental volume having some charge density, and of course this is a dielectric, and we are saying that this dielectric will also have some effect on the electric field strength, and therefore we are saying that the potential due to that elemental volume has two terms. One term that is the integral of the surface, the other term that is in the integral of the volume. And we are saying that these two terms denote the potential due to surface and volume charge distributions with densities rho PS and rho VS. So we are saying that elemental volume that is not purely in free space, but it is a dielectric, we'll have a potential at point O that has two factors. One is due to the volume charge density, and that volume charge density is due to the dielectric, and again a surface charge density. And therefore, these two are the one that we are characterizing, one by the polarization vector P with a unit vector AN, and the other one is due to the volume, is considered to be the divergence of the polarization vector due to the volume. So having said that, and just observing that we have two terms that constitute V as observed from point O, then we can make our final conclusions in regard to the effect of dielectric on the electric field in a dielectric. So we think that equation 526 right here reveals that where polarization occurs, an equivalent volume charge density rho V is formed throughout the dielectric, while an equivalent surface charge density rho PS is formed over the surface of the dielectric. We are saying a polarized elemental volume has some equivalent volume charge density that we are defining with rho PV, and another surface charge density due to polarization, remember, that can be defined as rho PS. And therefore, these two teleparameters, we are giving them a unique name. We are saying that the rho PS, due to the surface charge, allowed the surface or the elemental surface or the elemental volume is considered as bound or polarization surface charge density, and the rho PV is considered as volume charge density. Of course, again, bound volume charge density. And they are considered as distinct from the free surface and free volume charge densities, the one that we have made before, the rho S for the service and the rho V for the volume. Bound charges are those that are not free to move within the dielectric material. They are caused by the displacement. So just to make my story come to end, we said that we were trying to find out what is the potential at point O due to a polarized charge, or rather due to a polarized elemental volume. And we have found out that there is some bound service charge density and there is some bound volume charge density that is going to produce some field E that ultimately causes some E or some potential V to be experienced at our point of observation. And for that reason, therefore, we have said that the bound charges are those that are not free. So here we have bound charges that have polarization nevertheless, and that polarization is causing some potential at our point of observation. Free charges, on the other hand, are those that are capable of moving over macroscopic distance as do electrons in a conductor, and they are the ones that we can control. And therefore, if we consider the total positive bound charge on a surface bounding the dielectric, we are going to say it is equals to the polarization vector times the surface. Remember that we said the polarization vector has unit coulombs per meter squared. And therefore, if you multiply by the surface or by the area, therefore it will still gives you the charge in coulombs. So similarly, we have said that this is the charge on the surface of our polarized dielectric. But inside, again, we have said there is volume charge density. And therefore, if you multiply the volume or the bound volume charge density with the volume, then you, of course, get the charge. That's a fact. So we are saying if you apply the concept of divergence, which we have made before, we are able to find that we can define the bound volume charge to be equivalent to divergence or the volume integral of divergence of P as defined in equation 528b. Now, if the entire dielectric is electrically neutral prior to the application of electric field, and if we have not added any free charge, we notice that the dielectric will remain electrically neutral, and thus the total charge of the dielectric material remains zero. That means that the total charge that we have obtained on the surface, remember that this is the total charge, the charge Q B that we found on the surface, and this is the charge that we found inside the volume due to the bound volume charge density. If you add the two, we said that the dielectric remains neutral, and therefore the charge is equals to zero. Now we consider the case in which the dielectric region contains some free charge. And if that be the case, and if we define rho V as our volume charge density, then the total volume charge density rho T can be given by equation 529, which is the sum of the free charge density and the bound charge density. And if you remember again, we have already said that the volume charge density is given by Maxwell's first equation that says divergence of D is equals to rho. That is one of the equations that we have already met. So that is all we are applying. And if you remember that we have said rho D is equals to epsilon naught E for free space. Therefore, we can definitely agree with equation 5 to 9. And hence, from this equation, we can try to evaluate the volume charge, the free volume charge density as this value minus the one that is bound. And then we can actually remember that we can apply equation 5 to 8 that we have already met, that says the divergence of polarization vector. We have already said that the divergence of polarization vector gives us rho PV. That is the bound volume charge density. Therefore, of course, if we consider this to be at that, we can just replace this term with divergence of polarization vector P, and therefore these two terms being at the divergence, we can just put divergence outside, and therefore we have this. And what this gives us is a very important term, because we are saying that we know this to be rho V, and we have said that in the past, divergence of D is the one that gives us that. That is what we met before, and that is something we have been saying for a while now. And therefore, we can now equate the term. We can remove divergence altogether and remove the divergence and say that D is equals to this term. And that allows us to conclude that the net effect of the dielectric on the electric field E is actually to increase it, to increase the electric flux density inside the dielectric by the amount P. In other words, the application of E to the dielectric material causes the flux density to be greater than it would be in free space. And it should further be noted that the definition that we have already met before, which I think I've already written up here earlier, this definition that we defined in 435 for free space is a special case of this equation. And therefore, the general equation or the general expression of flux or electric flux density is defined as in this equation 531. Because we are saying in free space, the polarization vector is actually 0. In free space, there are no dipoles that are going to be disaligned, such that when you apply some field, they are going to be aligned, and therefore this does not happen in free space. And to finish up, we are saying that for some dielectrics, P polarization vector is proportional to electric field E, and we say that that case P becomes expressed as in 532. And I'm trying to tell you, I always try to make sure that you are able to pronounce the symbols that we use. This is a Greek symbol that is pronounced as chi. So we say that polarization vector P is equal to chi epsilon naught E. And we are saying that chi is the electric susceptibility of the material. And it's more or less a measure of how much or how well the material is sensitive to the electric fields. So the higher the susceptibility of a material, the higher the polarization the material would achieve, and therefore the more effect it will have on the electric field strength. The next item that we need to discuss today is dielectric constant and the dielectric strength. And this is rather simple. From the equation that we have met above, that is 531 and 532, we can combine these two by simply saying that replace P in this equation here, and therefore you are going to end up with D, or dielectric field, dielectric flux density, which is a vector, as epsilon naught E, a vector, plus psi E epsilon naught E. And of course, we can factor out epsilon naught and E. And when we factor out epsilon naught, we get equation 533. And then what we actually observe is that we can say D is a function of E, and therefore we have E equivalent to epsilon naught epsilon R. And now what we have new that we never had before is epsilon R, that is given by this term right here, which is epsilon 1 plus psi E. Therefore, once we have psi E, we have defined that psi epsilon R. We have already defined psi E as the material susceptibility. Therefore, we end up with defining the ER as the permittivity of the dielectric. Sorry, we end up defining the E as the permittivity of the dielectric, whereas the ER we define as the dielectric constant, or what we also refer to as relative permittivity. We already know the value of just a second. Sorry, someone interrupted. So I'm saying that we have already met that epsilon naught is given by 10 power minus 9 over 36 pi in farads per meter. And the new term that we have just met is epsilon r, that we have defined as the relative permittivity. And we are saying that it has a value that is always greater than or equals to 1. Because you can see there is a 1 here, we are saying that epsilon r will always be bigger than or equals to 1. And for free space, we are saying that the susceptibility of free space is 0, and therefore the epsilon r of free space is equals to 1. So the final comments, we are saying that the dielectric constant or relative permittivity epsilon r is the ratio of permittivity of the dielectric to that of free space. And of course, you can see in this definition that to be the case, that we are saying that it is the ratio of the permittivity of the medium to that, this is the permittivity of the medium to that of free space. That is the definition of dielectric constant epsilon r. It should also be noted that E epsilon r and psi E are dimensionless, whereas the epsilon itself and the epsilon naught are in farads per meter. And the approximate values of a dielectric constant of some common materials are defined in table B2, which I have actually brought it down here. So this is my table B2, and it's in your notes at the appendices. And therefore, it just tells you the approximate values of different materials. Glass, it has a maximum approximate value between 5 to 10, and a wood between 2.5 to 8, polystyrene 2.55, etc. The air itself, as I have mentioned, has the dielectric constant of 1. So it is good that we know the estimate or the approximate values of the dielectric constant epsilon r. So the last thing that I want to mention is that the theory of directrix we have discussed so far assumes that the directrix are ideal. That means, but practically speaking, no dielectric is ideal. And when ideal means that it never has breakdown. So we are saying that there's some concept that occurs called dielectric breakdown, and it occurs as follows. When the electric field in a dielectric is sufficiently large, it begins to pull electrons completely out of the molecules, and the dielectric becomes conducting. We have been saying that we are only aligning the dipoles or causing the non-polar atoms to stretch in a way that they form a dipole. But you're saying that when the electric field is sufficiently large, the electrons that we had here are pulled out of the atom, and they become free. When they become free, the dielectric starts conducting. And that period or the dielectric breakdown is said to have occurred when the dielectric becomes conducting. Dielectric breakdown occurs in all kinds of materials, both gases, solids, or even liquids. And it depends on a number of factors, such as the nature of the material, the temperature, the humidity, and the amount of time that the field is applied. The minimum value of the electric field at which electric breakdown occurs is called the dielectric strength of the material. So the minimum, so if we are increasing the electric field and the conductivity or the susceptibility is increasing as a function of psi, if at some point this begins conducting, this value of E is called the dielectric strength. And we say that the maximum electric field, the one that you're observing at E naught there, that a dielectric can tolerate it or withstand without breaking down, it is called the dielectric strength. So as I have mentioned, table B2 lists the dielectric strength of some common dielectrics. And since our theory of dielectrics does not apply after dielectric breakdown has taken place, then we are always going to assume that we are dealing with ideal dielectrics and avoid the issues that arise due to dielectric breakdown.